Hello everybody, so we are back now. Now that we know the vibrational contribution to thermodynamic equilibrium thermodynamic properties for macroscopic system containing diatomic molecules, let us get into the study of finding the rotational contribution to CV. Okay. For this, we know again we have to find out essentially first the internal energy, and from there you can get to CV, and for that what you need is Q, and that Q, for that Q, only the rotational contribution if we want, then it will be the Q rotational, molecular rotational partition function, and that we need to get. And for that again, this is nothing but summation over J G J e to the power minus epsilon J by KT. Okay, so the energy levels associated with rotational quantum number J, that is, as we know, J H cross square J into J plus 1 divided by twice I, where J goes from 0, 1, 2, etc. rotational quantum number, and then H cross is H by 2 pi, and then I is the moment of inertia, that is mu r square, where r is the bond distance, mu is the reduced mass. Okay, so mu is nothing but m1 m2 by m1 plus m2. Okay, where m1 and m2 are the for the diatomic molecules, so m1 is the mass of one atom and m2 is the mass of another atom in the diatomic molecule. Okay, and this distance from center of mass to center of mass, that distance is r. Now given this, and also we know what that Gj is nothing but, that is the degeneracy associated with a rotational level with rotational quantum number J is 2J plus 1. Now given this, so we can write out that Q rotational at a given temperature can be written as J equals to 0 to infinity, and 2J plus 1 e to the power minus beta is 1 by KT, and then H cross square J into J plus 1 divided by twice I, right? Where now this energy can be written actually in terms of for example, this part, as in the previous case, this can be written as something like H nu by KT, right? So if we write it as H nu by KT and then H nu by K, okay, H nu by K is the dimension of temperature. So in this case we are defining theta rotational, okay, that is whole thing divided by K, that is actually the this part is theta rotation, that becomes H cross square by twice IK, and that will be, K is the Boltzmann constant, that has the dimension of temperature. So this is the rotational temperature associated with the system, and that conventionally can be written as H nu by K, where nu means in this case it is B, the rotational constant. Okay, so what is the dimension of rotational constant? It must be something like frequency, because H into frequency, H nu, that is energy, divided by K, that is the dimension of temperature. So B is something which has got frequency dimension, that is inverse second, and that is H by because H square is H by H square by 8 pi square, 4 pi square, so it becomes 8 pi square I. So that is your B. Okay, so this B is the rotational constant in the kind of frequency dimension, that is time inverse dimension. Now this thing sometimes is also expressed in terms of centimeter inverse dimension, then naturally it is referred as B tilde in the centimeter inverse dimension, and that means you have to divide this by velocity of light, c, in centimeter per second unit, so that it becomes centimeter inverse, and that's why this is written as H by 8 pi square I into C. Okay, c is the velocity of light in centimeter per second. Then it becomes centimeter inverse. So this is the rotational constant, either expressed in terms of second inverse or in terms of centimeter inverse. So given any problem, you will have to be careful in which unit it is given, so that ultimately your temperature theta rotational is h nu by k kind of term, and that is hb by k, where b is in frequency kind of dimension. Okay, so be careful about that part. Now given this, our q rotational is something that can be now written, therefore q rotational as a function of temperature can now be written as j equals to 0 to infinity, and then it is 2j plus 1 into e to the power minus theta rotational into j into j plus 1 divided by t. Okay, so that is the expression in terms of theta rotational. Now this expression do not have a very closed form solution in general, but what we can do, if we know that these rotational energy levels j equals to 0, j equals to 1 and so on, like that, if these levels are relatively close by, that means with respect to the temperature available, if these energy differences between these states are much smaller, then at a given temperature kT is the kind of the order of energy that is available, then we can go from summation to integration, otherwise it is not possible. So for that analysis we have to find out what is the difference between the two successive energy levels, rotational energy levels, with quantum number j plus 1 and j, and that if you just substitute it here in this expression Ej and substitute in terms of B, and then it becomes like twice H B into J plus 1. How do you get that? That you get it from this expression, because this part H square B, that actually can be written as HB by K. Okay, so HB by, essentially this epsilon j is nothing but HB by K, j into j plus 1, and if that is the case, epsilon j plus 1 minus epsilon j is equals to HB by K, and then you have sorry, not K, no K is there, so K, forget this K part, so HB into J plus 1 common you can take, and then it becomes J plus 2 minus J, so that becomes twice HB into J plus 1, so that is what we have, twice HB J plus 1. Given this, so delta epsilon J plus 1 J divided by KT, that is the kind of consideration that we have with respect to KT, whether this gap is relatively smaller, and that essentially turns out to be something like this can be written as, you can multiply by K, so HB by K becomes theta rotational, so that is twice K theta rotational J plus 1 divided by KT, so that is essentially twice theta rotational by T J plus 1. So you can see at a given temperature, theta rotational is a characteristic of a diatomic molecule. So given that if this ratio is very small, then you can say this ratio is very small, then you can convert this summation into an integration. And typically, for example, if you do not have, say, smallest molecule like hydrogen in the diatomic molecule, and we'll come to that, if it is not so, for example, okay, let me stop here, video is going to stop, so we'll continue it again.